Hi everybody, Mr. Lee here. In this video, we are going to go over motion maps. Motion maps are a very powerful tool to help you understand the world around us. So let's begin. So in order to understand motion maps, I want us to go back to the buggy lab. Now, if you remember, for the buggy lab, we had a buggy, we let it run from one point to another, and we put down maybe post-it notes or a sticker or a piece of tape, something on the floor to indicate where the buggy was at a specific moment of time. And it kind of looked like this, right? So we put down our very first post-it note there, and we put down the post-it note as the buggy was traveling across a straight line. And let's just say, for the sake of this video, that we put down the post-it note every 3 seconds. So from here to here, it would have been, let's say 75 centimeters or 0.75 meters. That'll be our displacement. And if you remember from the previous video, we learned that displacement is the shortest point between 2 points, right? The final minus the initial position. And we learned that because it's a constant velocity model, it has to move the same amount of distance for the same amount of time interval. So for your lab, you should have gotten something like that. Now, where do motion maps belong, or where do we get motion maps? Now, that in front of you was what happened in the lab. Motion maps are a very powerful way for us to really visualize what happened without actually having to go through the lab. Okay, it's just a good way to communicate with others what's happening. So let's learn how to draw a motion map. Now, in order to learn how to draw the motion map, I'm going to write down a couple of rules that you should always follow on the left-hand side, and I'm going to start drawing the motion map on your right. And I'm going to leave that up there just to help us out. Okay, now for our lab, we used a buggy, right? We used that battery-powered car. Now, we could have very much used another object. We could use a actual car. We could use a human being. But the main idea is we need to represent whatever object that is moving with a dot. And that is actually our first rule. Represent object as dot. Okay. Now, in the world of physics, this is called a point particle. And if you're wondering why it's called a point particle, well, it just looks like a point, like that. Okay, so those red dots will represent where the buggy would have been if we were to have smushed the buggy into a single solid point, and it would have been right there. All right, so for our motion map, just got to try to match it up as much as possible. Those dots represent where the car would have been at a specific time interval. All right, second rule, always keep the time interval the same. Meaning, if you are representing each of these dots as a time interval of 3 seconds, like we did above, you got to make sure that you're counting by 3 seconds. So 3 seconds, 6, 9, 12, 15, right? It'll be really weird if you're going by threes and all of a sudden you switch it up midway through. Now, it's important to note that most of the time, your delta t will probably be 1 second, but for the sake of this video, this example, I just want to show you something different. So let's start off by indicating that this is going to be 0 seconds, and therefore this will be 3, this will be 6, and this will be 9 seconds. You don't have to always label like that. I'm just doing it so that you understand what's going on. Okay. Third rule, always have a reference line. Okay, this is very, very, very important. Our reference line actually explains to us what's happening in this scenario. And a reference line is simply a line. Okay, so I'm going to draw a horizontal line there. Why is it horizontal? Well, when I did the lab, I watched the buggy move across in a horizontal direction. Okay, and we're going to represent, or we're going to say this is our position line. Position, of course, being in meters. And you see this arrowhead? This arrowhead will tell me that this is going to be my positive direction. Okay, any sort of detail really, really helps. We can say this is positive, or we can even say that this is positive is going to the right. Okay, Now, a reference line is important, but so is the origin. So we'll say right there is the origin, or x is equal to 0 meters. So have a reference line and origin, okay, if possible. All right, next, arrows represent velocity, okay, and longer arrows, greater velocity, versus shorter arrows, which is less velocity. All right. Now, in order to show this, from your object, you're going to draw a velocity arrow or velocity vector. Vector is just another way of saying arrow, okay? Now, when you start to do this, if you like to use different colored ink, I do recommend that you use different colored ink because once we get more advanced, we will definitely add to these motion maps, and having different colors really does help you understand what's going on. All right, so we have different arrows. Now notice here that my arrows are of the same length, and that is key because with this model, we had a object, the buggy, and that buggy was moving with a constant velocity. All right, and the very last one, okay, the very last rule is you should always verbalize the scenario. All right, so the reason why we want to verbalize the scenario is when you're trying to solve problems and you have absolutely no clue what to do, oftentimes starting off with a verbal really helps out with trying to really decipher with what's going on. So for this verbal, I could make it simple as object starts at origin, okay, or 0 meters, moves to the right, okay, and so I can say for every 1 second, or we can say for every 3 seconds, object moves 0.75 meters, right? And that's just another way of verbalizing our velocity. Okay, so for every 3 seconds, this object moves 0.75 meters in the positive direction. All right, and that's that. Yeah, so here's a couple of big main ideas here. All right, these motion maps, they don't have to be exact. They don't have to be very precise. They are just a way for you to communicate with others with what's happening. There's good motion maps and there's great motion maps, but the only thing that you really care about is, does your motion map accurately depict with what the scenario is actually supposed to be depicting? Okay. Yeah. And so another way to think about it is, if another physics student, or if I were to take a look at your motion map, I could immediately tell what is happening. Okay, so it should be nice and clear and easy to understand. And that's that. That's motion maps. So let's take what we just learned and try to apply it to a new motion map. All right. Let's do this. I'm going to draw a reference line. Okay, we'll say right here is the origin. Okay, and we will have just the object moving to the right. All right, and see what I do right there. Oh, look at that. All right, so here is my motion map. All right, now I added a couple of new things there to really help you understand with what's going on. And this is why I'm saying the verbalization of it, of the motion maps, is where things go really, really handy. So I'm going to first describe this first part that I just highlighted right there. Okay, I'm going to say object starts at origin, moves to the right with constant velocity. Okay, and if we actually knew the velocity, we could write it down. So I'm just going to make one up. For every 1 second, the object moves, let's say, 5 meters. All right. Now I'm going to verbalize these dots there, and I'll represent that with this highlighter here. All right, those 3 dots. So I can now say object comes to rest, which is a fancy way of saying it just stops. And I'm going to say for 3 seconds. All right, so the object comes to rest for 3 seconds. Okay, and we know that because there are 3 dots there. So if we want to make this verbal part up here a little bit more specific, we can even say, so this will be time is equal to 0 seconds. This will be, let's say time is 1 second. This will be time 2 seconds, time 3 seconds. All right, so we can say for every 1 second, the object moves 5 meters for a total of 3 seconds. And let's see, 5 meters times 3, what would that be? And 15 meters. All right. And then the object comes to rest for 3 seconds, right? And we see that with those 3 dots. And finally, the last part, let's do that in purple. Yeah. Boom. All right, let's verbalize that part. For that part, we can say object moves to the left, aka the negative direction, okay, with a slower velocity. And if you're thinking to yourself, how do we know it's slower? Well, look at the size of the arrowheads, okay? What is the size of the arrows? The arrows themselves, I drew them smaller. And also, like the amount of spacing between each dot, it's less. The object moves to the left, the negative direction with a slower velocity. We can say for every 1 second, the object moves, let's just say 1 meter for a total of 3 seconds and 3 meters. Okay, and we can also say the object does not return to the origin. And boom, wow, this here is really solid. So what I'm going to do next is I'm just going to highlight the different parts of the motion map. Let's start off with the yellow part. Object starts at the origin, moves to the right with constant velocity. For every 1 second, the object moves 5 meters for a total of 3 seconds and 15 meters. Good. All right, so that's the part of the yellow. And next we did the part in the green. The object comes to rest for 3 seconds. Now here it's important, we could even write down that the velocity for rest means 0 meters per second. A good way to help you memorize that, and a good way for those that are reading this statement to know what you're talking about. All right, last statement. Object moves to the left, the negative direction with a slower velocity. For every 1 second, the object moves 1 meter for a total of 3 seconds and 3 meters. The object does not return to the origin. And my friends, that's that. That's how you draw a motion mass, and that is how you use a verbal to describe what is happening. Okay. Now, if I were to tie this all together again, we could also include the different kinds of graphs. For example, we could do a position versus time graph, and that's what you're going to be seeing in your worksheets and your practice. All right. Until next time. See you later. Bye-bye.